Welcome to Cool Guy Podcast. What is actually this black hole?
We are tackling, I think, the ultimate cosmic mystery. What actually is a black hole?
Right. It's a question that, gets at the very edge of physics.
It really does. So let's start with the basics. What's the one-sentence definition?
Simply put, it's a spot in space where gravity is so strong that nothing can get out.
Nothing at all.
Not a thing. Not even light, which is, the fastest thing in the universe.
Okay, let's unpack that. Your sources are clear that this isn't just a hole, it's a physical object.
Yeah.
A super, super dense one.
Exactly. It all goes back to Einstein. Mass and energy actually warp the fabric of space and time.
The classic bowling ball on a trampoline analogy.
That's the one. Now, with a black hole, imagine something so dense, it doesn't just dent the trampoline, it rips a hole right through it.
Mm-mm.
The warp is so extreme that all paths, even for light, just lead back in.
So gravity has completely won?
Gravity has won, and that win creates two key features. You have the singularity right at the center.
The infinitely tiny point with all the mass.
And then you have the event horizon.
Which isn't a physical surface, right? It's more of a boundary.
It's a point of no return. Once
Yeah.
you cross it, all the math says you are not coming back out.
This, I think, leads to the biggest misconception out there, the idea that they're cosmic vacuum cleaners.
Oh, yeah. That they just suck everything in from galaxies away.
But that's not true, is it?
Not at all. A black hole follows the same laws of gravity as anything else. I mean, if you replaced our sun with a black hole of the exact same mass,
We just keep orbiting it.
we'd keep orbiting. It would get very cold, but we wouldn't get sucked in. Matter has to drift very close to fall in, and even then, it's a slow, gradual process.
And what's wild is that they come in such different sizes.
Oh, wildly different. You have your stellar black holes, which are maybe a few times the mass of our sun. They're the leftovers of a giant dead star.
And the other end of the scale.
Then you have the supermassive black holes, millions, sometimes billions of times the mass of the sun, sitting at the heart of pretty much every big galaxy.
Including our own. So if light can't escape, how on earth do we even find them? What are we seeing?
We're not seeing the black hole itself. We're seeing the chaos it creates around it.
Like the crime scene, not the culprit.
Perfect analogy. Sometimes we see light from a star behind it get bent, what we call gravitational lensing.
Okay.
But the big one is the accretion disk. That's all the gas and dust swirling around the event horizon, getting superheated by friction and glowing incredibly brightly before it falls in. Missions like SOFIA study that heat, that glow, to figure out what's going on.
All right, now for the really weird stuff. The effects of getting close. We have to talk about spaghettification.
Right. It's as bad as it sounds. The tidal forces are so extreme that the gravity on your feet would be exponentially stronger than the gravity on your head.
So you'd be stretched.
You would be stretched into a long, thin strand of atoms, like spaghetti.
Yikes.
But here's the paradox. For a much, much bigger, a supermassive black hole, the tidal forces at the event horizon are gentler. You could actually cross it totally intact.
And then there's the other bizarre effect. Time itself.
Time dilation. As you get closer to the black hole, time for you slows down relative to someone watching from far away.
So to me, watching you fall in, you would seem to slow down, get dimmer, and just freeze at the edge. Forever.
Exactly. But for me, falling in, time would feel completely normal as I cross that horizon.
So we have these objects that are, in a way, very simple, just mass and spin, but they just break our understanding of space and time.
I really do. And maybe the biggest mystery of all is what happens at the end. Stephen Hawking theorized that they aren't actually eternal.
They evaporate.
Very, very slowly. They leak a tiny amount of energy called Hawking radiation. Over trillions and trillions of years, they could just disappear.
So what happens to everything that fell inside, all that information, all that history?
That is probably the deepest unresolved question in physics today. Where does it all go?
A mystery waiting for one of you out there to solve. Thanks for joining us for the deep dive.